Today's experimental mathematics seminar speaker is our own Natalya Ter-Saakov, who will speak about origami flip graphs of single vertex crease patterns. As usual, you're welcome to unmute yourself anytime you have a question and then mute yourself back. Thank you.
Thank you, Dr. Lee. All right, so origami flip graphs of single vertex crease patterns is a lot of words that perhaps you know individually, but we'll start at the beginning and go through them slowly. So hopefully, this is an overview. Hopefully you all know what origami is. It's paper folding. If you want a more rigorous and mathematical description, we think of origami as being a planar graph embedded in a subset of R2 with straight line segments as the edges or creases, and a flat folding as a continuous non-differentiable function from that, a continuous function that is non-differentiable along the edges of our embedded graph and is an isometry on the faces. But it's what you think of. You have a crease pattern, a set of creases and vertices that you'll be folding along, and you fold all of them. So with a crease pattern, which looks like, you know, what one might imagine, I could draw an example. This is a very small crease pattern. It has 4 creases, 1 vertex. With that, you want perhaps some instructions on how to fold this. And these come in the form of, well, step by step, if you're being nice, or if you're being slightly less nice, a mountain valley assignment. So if we take that same crease pattern and give each crease either a mountain or a valley, a 1 or a -1, that tells us how to fold it. If you're not familiar, a mountain looks like this with your paper. It's when you fold away from you. And a valley looks like this. So this is 2 pieces of paper folded as a mountain and a valley, or a +1 and a -1. If that sounds good to everyone, then we care about flat foldable origami. And to have that, we want, you know, to be able to fold it, for which there are some rules. The first is Kawasaki's theorem. It says that if you're given a crease pattern, then around any given vertex, the alternating sum of the angles sum to 0. So, for example, this crease pattern I can draw, but you will never be able to fold along exactly these creases. Whereas this crease pattern looks somewhat similar, and this one you can fold successfully. So Kawasaki is necessary to be able to fold it at all, but we'd also like some rules on mountain valley assignments that are, you know, possible for a crease pattern. And the first of those is Michaelas' theorem, which...
How are the angles measured in that prior statement? It wasn't clear how you were measuring the angles. Some of them are positive, some of them are negative?
Well, we measure our angles in degrees, radians, choose your favorite measure of angles, and then we're going to take the alternating sum. So here, I don't know, maybe this is a 60-degree angle, this one's 120, this one's 60, and this one's 120. So our alternating sum will be 60 minus 120 plus 60 minus 120, which is...
Why can't you fold that? Well, Natasha, why can't you fold that one on the left? It looks like you just fold it once and then fold it again, and that's what you'd get with a piece of paper.
So feel free to take a piece of paper and try it. I can fold it the first time. But then if I want the other 2 creases, if I do something that looks like this, it ends up looking like the one on the right. That is maybe still there for you. I thought I erased the one on the right. And you have this bird's foot that I'm showing in my image. To try to get both of those fold at the same time, you're going to run into the problem that there's just not enough paper to go back and forth. The proof of Kawasaki's theorem, or the nicest proof that I've seen of Kawasaki's theorem, is very clean and very pretty. It looks something like, look at your paper from the outside. It's going to look something like this when it's folded, plus or minus, I gave it some extra thickness. And if you're alternating some of the angles don't add up to 0, then at the end, you're not going to end up in the same place.
I just folded a piece of paper and it looks exactly like the one on the left.
Do you show?
I can't show it, no. Can I show it?
You could hold it up to the camera. A little bit further back. Yeah, so you want those creases to be folded simultaneously.
Well, I folded it once.
Yes.
I folded it the other way.
Sure. But can you do them simultaneously, right? When we have a crease pattern, we want it to fold along all of the creases shown and just those creases shown at the same time. Otherwise, you're doing things one at a time and that doesn't count.
If I fold it like that, then fold it again, if I unfold it and then fold it, that doesn't count?
No, you want all of the creases to be folded simultaneously.
Okay.
Okay. I'm having slight technical difficulties where I don't know if you can see a difference in my slides, but my attempts to advance them is not working. Give me 1 second. Yes, please, thank you.
We have Kawasaki's theorem slide.
Yes. Now, do you also see Michaelas theorem?
Yeah,
Yeah.
sure.
Great. Okay. So Michaelas theorem is a statement that we need about flat foldability and mountain valley assignments. It tells us that the number of mountains plus the number minus the number of valleys is going to be plus or minus 2. For similar reasons of if you look at your folded entirely around one vertex crease pattern, it'll look something like a zigzag thing that hopefully matches up. And for it to match up, you must, turn left and turn right almost an equal number of times, except for the 2 turns to make it a full circle. Kawasaki's theorem is necessary and sufficient for a given vertex to fold flat. Michaelas theorem is necessary for mountain valley assignments, and adding in big, little, big makes it also sufficient. Big, little, big says we're going to look at our smallest angle and have rules about how many mountains and valleys you have on those. So if, for example, we look at, let me choose a better contrast color. This crease pattern right here, pretend I drew the angles correctly. If you try to make both of these mountain folds simultaneously, then these 2 blue faces will attempt to both fold over onto the small face here and attempt to occupy the same space at the same time and try to self-intersect. Not allowed. So a valid folding of this must have one of these be mountains and the other one be a valley. Similarly, if we have more creases, more faces in a row that have small consecutive angles, they must have mountain valley either plus or minus 1 if there's an even number of them, or 0 if there's an odd. So these are rules that we know about mountain valley assignments. Any questions on either of these? Great.
And how old are the theorems? Are they classical?
Yes, these are fairly classical, fairly foundational. Kawasaki's has been around for a while and has been proven independently a couple times. Michaelas also has been around for pretty much as long as this field has been around. There have been newer, nicer proofs than the originals. I know a proof by Tom C. Hull for both Kawasaki and Maikawa.
Thank you.
Big Little Big is a little bit newer, but not by much. So these are rules for crease patterns. They tell us about local flat foldability. Unfortunately, local flat foldability is not the same as global flat foldability, unless you only have one vertex, because you start having some issues with paper self-intersection from different vertices coming over one another, but that's okay. We looked at single vertex crease patterns. They were the same for us. So a mountain valley assignment, to review, is valid if it is locally flat foldable. And we're going to notate the number of valid mountain valley assignments for a single crease pattern as C of B. So what did we look at? We looked at face flips. Given a mountain valley assignment for a crease pattern, a face flip is a reversal of parity of the creases bordering that face. A face flip is valid if it results in a new mountain valley assignment that is also valid. So one way that it could be not valid is if you flip something and the resulting mountain valley assignment would violate Maikawa's rule. Here's an illustrated example. The bolded lines here are mountains and the valleys are unbolded. You can see that from this mountain valley assignment for this crease pattern, we can flip face A and everything's all good. We can place flip F and this still is valid. But if we flip face B, we now have only mountains and no valleys, and that has mountains minus valleys equals 6, which is not valid. So this is an example of flippable faces. And so if we are given a crease pattern, we can draw an origami flip graph. Where every vertex is a valid mountain valley assignment of that crease pattern, and every edge is a face flip between two valid mountain valley assignments. So
Natasha, could I ask you something? The previous slide, when you did the flip of the A flip,
yes.
Could you explain exactly what happened? You flipped, how did you get that picture on the right from the one on the left? What did you do?
Absolutely. So we took the creases that border face A and we changed their parity. So multiplied by -1 or changed from mountain to valley and valley to mountain. So the crease between A and B switched from valley to mountain, and the crease between A and F switched from mountain to valley. And that was all the creases that bordered A. So then we were done.
So the bold became thin and the thin became bold, Neil.
Yes.
Yes. Thank you.
Great. So origami flip graph illustrates these changes. Here are some examples. Here's a small origami flip graph for this degree 4 single vertex crease pattern. You can see we have the different mountain valley assignments drawn. Again, bold mountain, unbolded valley, and the face flips. This one's not labeled, so figure it out. Here's a slightly bigger example. Still a degree 4 crease pattern, slightly bigger origami flip graph. Bold mountain, unbolded valley. And the last possible degree 4 crease pattern and its origami flip graph. When I say last possible, I mean has a different origami flip graph from the others. You'll see that this one is even more complicated. Great. So this is how we constructed the origami flip graphs, and we attempted to present some general characteristics of them. What can we actually say? Well, we can start by counting the vertices. This was an already solved problem because the number of vertices is the number of valid mountain valley assignments. Michaelas rule, along with big little big, tell us the number of mountain valley assignments. And how they do so is we have a way of recursively folding. We're going to start with the smallest angles, assign them mountains and valleys, fold them up. We get a cone, look at the smallest angles that are consecutive, assign mountains and valleys according to big little big, fold up, rinse and repeat. So an illustration of this is here. We started with this crease pattern all the way on the left. It has a smallest 10-degree angle. So big little big tells us that that 10-degree angle must have one mountain and one valley bordering it. And we can have two ways of assigning those. Then we fold it up and we get this. Note that the way we folded it looks kind of like a zigzag. So our new angle is going to be 15 minus 10 plus 15, which is 20. Now we have two smallest consecutive angles, these two 20-degree angles. Big little big again applied tells us that mountains minus valleys is plus or minus 1. So we need two of these to be mountains and one to be a valley, or vice versa. This gives us 6 possible ways to assign mountains and valleys to these creases. We do so, fold them up. We have a smallest 60-degree angle, assign mountain and valley, fold, and now we have two 90-degree angles, and we're folding it together, either both mountains or both valleys. So that's 2, and multiplying these numbers together, you'll get the number of possible valid mountain valley assignments for this crease pattern. So that gives us an upper and lower bound on our number of valid mountain valley assignments, C of V. Our lowest bound is 2 to the n. And our upper bound is when we have all equal angles and we're just choosing n minus 1 of them to be minority and then deciding whether minority means mountain or valley. So that was recursive folding and how we count the number of vertices. Thank you. We also discovered that all origami flip graphs for single vertex crease patterns are bipartite. This is not true in general. You can get a fairly simple, a very simple crease pattern that has less vertices and 2 vertices. And the origami flip graph for this crease pattern is not bipartite. You have a 3-cycle. But for the single vertex crease pattern, they're nice and bipartite. And then we decided to look at, connectivity. And we did this while looking at the smallest C of E case, 2 to the n. Right, this arises from at every step in our recursive folding process, we have 2 choices, meaning we had a smallest angle. And so then another smallest angle, and at the end we have 2 equal angles and we fold them up. So because these choices are always independent, we end up getting a hypercube or a couple copies of a hypercube. We discovered that, for example, this crease pattern has a disconnected origami flip graph. Because we have, smallest angle at C. But this means that if we've already decided whether to assign mountain or valley to the creases bordering C, we can never flip face B, because if we flip face B, then C would no longer follow big little big. We wouldn't have one mountain and one valley. Similarly, we can never flip D. And then once you fold up C, we see we can't flip A or E because F is the smallest angle. So here we can only flip C or F and can never get from having majority mountain creases to majority valley creases by just these flips. So unlike this case, the very similar looking crease pattern on the next slide, which refuses to appear, apologies, has a connected cube hypercube as its crease pattern. And here we can flip all three faces independently. So we explored what makes something connected or disconnected. And this idea of having faces that can never be flipped led us to talk about never flippable faces. And if you track where the never flippable faces are, you also sometimes get restricted creases, which are never flippable faces that have been folded up and are now hidden in a crease. You can see some on this photo. So we marked the never flippable faces with do not signs, and then we folded up. This became a never flippable face. And then this got folded up into this crease, which is a restricted crease. And if you have enough never flippable faces or restricted creases interacting with one another, i.e. touching, then your origami flip graph becomes disconnected. So that characterized the connectivity, after which we went to go look at the largest C of V case, otherwise known as the all equal angle case. So if we have all equal angles, our only restriction is Michaelas theorem, that mountains minus valleys is plus or minus 2. So our number of valid mountain valley assignments is 2 times 2n choose n minus 1. We're going to call these crease patterns a sub 2n, the crease pattern with 2n equal angles. And our only restriction on what can't be flipped is if you are a face surrounded by minority creases, because flipping that would violate Michaelas theorem. If we were to think back to this image where we had the all equal angles case for 6, B is surrounded by 2 minority creases, 2 valleys, and flipping that violates Michaelas. A has 1 of each. Flipping that just keeps the number of mountains and valleys the same. And flipping something like F changes 2 majority creases to what were previously minority creases and just switches what majority and minority are, still leaving M minus V equal to plus or minus 2, and just changing the sign. So that reduced the question of, maybe we'd like to count the number of edges in this case. Sounds like a reasonable thing to count. We tried drawing one of these. This one has 84 edges. It's very pretty, has lots of rotational symmetry, and is terrible to draw. So this was not the way to go, but we ran some simulations and found some numbers. We have a formula for n. That one's easy. A formula for the number of vertices we have. And it's even in OEIS. Life is great. And then the number of edges. We tried putting it in
this sequence existed before, or
the number
it's
of
a new
vertices,
interpretation, or it's a new sequence?
yes. Number of vertices existed before. It's been around for a while. This is known. Very easy formula. Everything was great. This was known before us. Number of edges was not known. We tried putting it in OEIS. OEIS gave us nothing. We were very surprised. That hadn't happened to us before. Got stuck for a while. Then I came here and was talking to Robert and was like, I have this sequence. I don't know what it is. Robert went to lunch and came back with this formula. And I went, now there's a formula. All that's left is to prove it. So by looking at the expected degree of every vertex, the expected number of flippable faces, or the expected number of not flippable faces is what I actually looked at. Using linearity of expectations, some indicator variables, a little bit of probabilistic method, I successfully proved Robert's formula. So now we have that. It's not yet in OEIS because I got slightly stuck on the put it in part, but I will make Robert help.
So Robert conjectured it and you proved it.
Yes.
Ah, that's nice.
And then we also decided, well, now we have a number of edges. It comes from, the expected value of the degree of every vertex times the number of vertices. You can sort of see that here. Perhaps we can find the number of vertices of each degree. And we found a formula for that, proven by a collaborator named Jonah. So the number of vertices of degree k, where k goes from n+2 to 2n, is 4n over n+1 times n+1 choose k minus n minus 1 times n minus 2 choose k minus n minus 2. And this was great. We now know how many vertices are in this graph, how many edges are in this graph, and how many vertices of degree k are in this graph. This is very useful. We also have some other useful information. We know that this graph for the all equal angle case is always connected, and that it always has diameter n. Proving that it has diameter at least n is very easy. If you think about a mountain valley assignment and its exact opposite, in other words, looking at it from below, every crease switched parity, and we can only switch parity of creases, by flipping one of its adjacent faces. So if you can, you just flip every other face, and that gets you things that are n apart. Every face flip flips only 2 creases. We have 2n creases. We need n flips. But proving that n is sufficient was a little bit harder, did that as well. And this is great, but it leaves the question of why are we interested in this all equal angles case so much? That's the bit that I'm excited about. The all equal angle case contains, as a subgraph, as an induced subgraph, all of the smaller single vertex crease patterns. In fact, multiple times because of the way that we do this. So let me show you an example. If we look at this small all equal angles degree 4 case, and then look at the crease pattern that looks like this. It's called a bird's foot. We're going to label this face A, this face B, this face D, and this face C. Big Little Big tells us that the creases around D and C have to have at least either one valley and 2 mountains, or 2 valleys and 1 mountain, meaning that this case here and this case here are not valid mountain valley assignments for our slightly different crease pattern. If you just imagine on each of the mountain valley assignments, shifting the horizontal creases a little bit down to match my drawn picture. But if we look at the remaining 6 mountain valley assignments, vertices in our graph, and the edges that continue to exist, so removing these 4 edges and these 4 edges, that graph is the origami flip graph for the bird's foot crease pattern. And so by studying the all equal angles case, we feel like we have a better grasp of this slightly shifted or every other crease pattern on a single vertex. So there's lots more to be done here. Obviously, we can look at origami flip graphs of multi-vertex crease patterns. There are also tons of cases in between the all equal angles case and the smallest C of V case that haven't been fully explored. We have not much information about this. There are also many questions that you can ask about the all equal angles case. For example, how many Hamiltonian cycles does it contain? Any, many, etc. These are the things that we're continuing to think about with this question. I'd love it if my slide flipped, but it's not agreeing to. Thank you. Any questions?
Oh, thanks so much. Let's thank Natasha again for a beautiful talk. And we have plenty of time for questions. So the Hamiltonian path. So you want to enumerate how many? Or what?
Yeah, so a good question is, are there any? And our intuition says yes. And then if there are, it might be nice to count them. Certainly, if we want to motivate this through non-mathematics, there are people who care about origami and robotics and have been working on making very small robots that out of some nanomaterial on a nanoscale where you add some electricity and they fold up or unfold depending on how much electricity you have. But also bigger robots, things with heart stints and sending solar panels into space. And all of these people care about, what if my robot suddenly decides to fold in the wrong way? That would be unfortunate. And so this question of face flips is one way that a robot could fold wrong, and talks about, how easy it is to make a mistake and end up with something that looks completely wrong.
More
So
questions
many
for Natasha?
questions could ask about them. I tend to like very theoretical graph theory questions, such as how many Hamiltonian paths, that I'm not sure that the roboticists care about. But I'm
So the proof of the number of edges, was it difficult?
It had some creative steps, and I think we tried many other methods to come to it. Also, it was hard to prove something when we didn't have a formula.
Yeah.
But once we had a formula, an idea of it looks related to the number of vertices, which we knew, the idea of linearity of expectations, and we can find the probability that a given face is flippable or not flippable, whichever one you prefer. After that, it was not that hard.
Interesting. Other questions for Natasha? So I have
Is there a preprint of what you did?
Not on archive yet, is the correct answer.
I'm still puzzled about my first question. I'm sorry to be stupid about this. If I hold up my piece of paper again.
Yeah, perhaps I can stop sharing unless anyone wants the slides. I'll stop sharing and then I'll start sharing again.
So I take a squared piece of paper and I fold it once along the red line.
Great.
And then I unfold it and fold it again along that crease, and I open it up and I have something that looks like this.
Right.
And that doesn't satisfy your conditions.
Correct. So a crease pattern is flat foldable if by folding along exactly the creases given, so all of them and no others, we end up with something flat. So I can try, oh, I don't know. Trying them all valley doesn't make much sense. I'm never going to get anywhere because all of the paper tried to collapse in on itself, but maybe I'll try making this one a mountain and the other three valley. And so this is a mountain, it goes in, this is a valley, and this is a valley, except I'm still not able to push it flat. Or if I do try to shove it flat, I'm going to end up with some new creases that weren't there.
Okay. Yeah, that's clear. Okay.
And so if we look at, for example, the bird's foot, I have these three be valley and this one be a mountain. And then they do successfully fold flat and I can put it in a book and I folded along exactly the creases that were given to me, these four.
Good. Yeah. Thank you.
So,
and of course, Neil, you're very close. We could just meet up and fold some paper together if you'd like.
Absolutely.
yes,
Yeah.
yes.
You're still just down the street, right?
Absolutely.
So most people, when I was learning to fold or any origami, I certainly got my origami with step-by-step instructions. But apparently, if you get to a high enough level, they just draw you a crease pattern. And sometimes they're nice enough to give you some mountain valley assignments. Sometimes they aren't. And they're really banking on the fact that we are humans and know how to do these things because flat foldability is an NP hard problem. If you just give a computer even a crease pattern with mountain valley assignments, and ask it, is this flat foldable? This is NP hard. There are some good articles on this with reducing it to 3-sat in very pretty ways because it's origami and it's all pretty.
So this proves human superiority.
Yes, or at least ingenuity. Or really we're banking on the fact that the person who gave us the crease pattern also thinks it's flat foldable. So if you just try hard enough, it's in there somewhere.
There's a famous Eric Demaine thing in MIT. Is it related what he does to you stuff?
Yeah, he does many different things with origami and some with other puzzles, but yes, these are very related. I had a great time in his class.
Could you recommend some survey paper that gives background on what you talked about?
Absolutely. I can get it to Robert and Dr. Z and they'll send it out or post it with the slides and the video, if that works. I don't have one, at my fingertips on my computer that I can just link.
Yeah, you can add it to the slides if you wish. Yeah.
Great.
Yeah, that's good. Okay, more questions for Natasha? Well, thanks so much for coming and thank Natasha for a great talk. And this ends this seminar. Thank you. Thank you. Robert, please end this meeting. Thank you.